In this video, we're going to use the Pythagorean theorem to find the distance on a coordinate plane. To find a diagonal distance on a coordinate plane, one of the things we could do would be to create a right triangle where the diagonal distance is the hypotenuse, or in other words, the variable c. Then, once we've created that right triangle, we can use the Pythagorean theorem to calculate the diagonal distance. So again, this is most helpful on a coordinate plane when we are looking for a diagonal distance that can't easily be counted by looking at the units on a graph. We can easily count vertically and horizontally, but if we're looking for a diagonal distance, that's where we need to create for ourselves a right triangle where we're solving for the hypotenuse. Let's look at an example, and if you're following along on the student handout, this is the first graph. So we have points A and B, and we want to find the distance between those points, and we're going to round to the nearest tenth. So again, A and B, if I were to draw this path, that's a diagonal distance, and I really can't count using the lines on this graph because of the fact that it's diagonal. What I could do, though, is draw the path vertically and horizontally from one point to the other, and what I've just done is I have created for myself a right triangle. I can easily count the units vertically and horizontally. So for example, this distance is 1, 2, 3, 4, 5. And then the horizontal distance is 1, 2, 3, 4. So basically in this right triangle, if I wanted to redraw it here, I have the legs are 5 and 4 units, and then we're solving for the diagonal distance c. So we need to set up the Pythagorean theorem where we substitute 5 and 4 for the variables a and b. So we can rewrite this as 5 squared plus 4 squared is equal to c squared. Now we'll simplify. 5 squared is 25 and 4 squared is 16. Then we find the sum on the left. If I add 25 plus 16, that equals 41. And we don't want c squared, we want just the value of c. And I actually prefer to write the variable on the left here. And so to undo squaring a number, we take the square root, and what I do to one side of an equation, I have to do to the other to keep this balanced. Now the square root of 41, we want to round to the nearest tenth, so I would round this to 6 and 4 tenths. That means that the distance between points A and B is about 6 and 4 tenths units. Let's do one more example, and on the student handout, this would be found on the back. It's giving us two ordered pairs, and we want to use the Pythagorean theorem to find the distance between those points. So my first step is going to be to plot these points. The point negative 6, 1 is right here in quadrant 2, and the point negative 4, 5 is also up here, right in quadrant 2. So let's call this point A, and this is point B, and we're looking for this diagonal distance that we really can't count just by looking at the graph. We're going to have to use the theorem. So I'm going to draw a right triangle from one point to the other. And so I can count the length of the legs. I can see that this first leg is 4 units. And then here, this is 2 units. And then we are missing the value of the hypotenuse, or c. So again, if it helps you to see that drawn out, we have legs 4 and 2, and we are looking for the hypotenuse. So let's set up the Pythagorean theorem. And I'm substituting 4 for a, so 4 squared, and 2 for b. And now 4 squared is equal to 16, and 2 squared is equal to 4. And then 16 plus 4 is 20. And so if 20 equals c squared, I can find the value of just c by taking the square root of both sides. And the square root of 20, if I round that to the nearest tenth, that gives me 4 and 5 tenths. And we'll just put units. So we always want to make sure that our answer is reasonable. If this was 4 and 5 tenths, it's reasonable compared to the values 4 and 2, and it's also the longest of those 3 values. So that's a great way to check our answer and be confident that we solved correctly. Way to go finding the diagonal distance on a coordinate plane by using the Pythagorean theorem.
So our job here says to graph a right triangle with these 2 points being the hypotenuse. So what we do is we just click on one point, and I'm then going to move my mouse until I'm directly underneath the other point, and that is the horizontal distance, and then I'll click again. That's created essentially the base of this right triangle. Now I'm going to click on this corner, and then I can move anywhere, but really I need to move vertically because it's easy to count vertical distance. It's 1, 2, 3, 4, 5. Click. So I've created this right triangle. Now that I have, I'm supposed to name the legs and then name the hypotenuse. So it doesn't matter in which order we put the legs. This leg on the bottom is 1, 2, 3 units. That's the horizontal distance. And then the vertical distance we counted earlier was 1, 2, 3, 4, 5 units. So if we have a right triangle whose legs are 3 and 5, what is the hypotenuse? So let me actually just redraw that right triangle. This is a Pythagorean theorem problem. If we have a 3 and a 5, then what is the hypotenuse C? Well, we're going to do 3 squared plus 5 squared equals C squared. 3 squared is 9, 25 squared, 5 squared is 25. And then we do 9 plus 25, which is 34. And our last step is to solve for C. So to solve for C, we'll take the square root of both sides. And the square root of 34 is the answer in simplest radical form. So we'll press the square root button, actually. So I should click in this box first, then press the square root button, and then type square root of 34. If you're curious what that is, the square root of 34 is a distance of about 5.83 units. So the hypotenuse will always be the longest side, that's longer than 5. But in this case, the exact way of writing it is as the square root of 34. Now, distance between 2 points. Graph a right triangle with the 2 points forming the hypotenuse. Use the sides, find the distance between the 2 points to the nearest tenth if necessary. So our goal is to actually create a right triangle out of this little dotted line. So the distance between 2 points is the same thing as saying the length of the line that connects those 2 points. So to find a diagonal length, we should consider it the hypotenuse of a right triangle. So in order to draw a line, we will click once and then click somewhere else. That draws a line. Click, click, that draws a line. Now, of course, we don't want the lines there, so we can erase our lines by clicking them with that little circle with the line through it. So to draw the height, what we should do is start here, click once, and then go down, straight down to a y value equivalent to the y value of this yellow point. So straight down, but down to that. If you click, that represents the height. Now we're going to click again once, and then go over straight to the right to that point. It says we may now answer our questions. So our goal was to find the length or the distance between the 2 points. But in order to do that, we're going to want to find the length of this leg and the length of this leg. So how do we do that? Well, for one, we could count. But I do want to show what is the distance here. This is an x-coordinate of -7 because one of the points up there had an x-coordinate of -7. The other one has an x-coordinate of 2. So how far is it from an x-coordinate of -7 to an x-coordinate of 2? The slow way is to just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means this leg is 9. So I'm actually going to write leg 1 as 9 if leg 1 is the bottom. It doesn't matter which one is leg 1 and leg 2. But I do want you to see that we get the same answer as if we subtracted the two x values. So if we did 2 minus -7, that's the same thing as 2 plus 7, which is the same thing as 9, which just so happens to equal the width of this right triangle. Now, as far as the height is concerned, let's see. Well, how do we find the height? Well, the height is going to be based on the difference in the y values. So if this y value is +6, and this y value down here is -6, how far away is a y value of 6 and -6? Well, we could count 1, 2, 3, 4, 5, 6 just to get to the x-axis, and then 1, 2, 3, 4, 5, 6 more to get down to -6. So 6 plus 6 is 12. So that means this whole height is 12. So the other leg is 12. But how could we have used the coordinates? Well, to find the difference between a y coordinate and another one is just to subtract them. So if we did one y coordinate, this one, minus the other y coordinate, minus -6, that's the same thing as saying 6 plus 6, which is equal to 12, which is, of course, the other leg. So what we have created is we've created a right triangle, and we know that its height is 12, or one leg is 12 and one leg is 9. So now that we know the legs, our original goal was to actually find the distance between the points. But since we have drawn a right triangle, we can use the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared is equal to c squared. So doing this, we're going to plug 12 squared plus 9 squared is c squared. 12 squared is 144. 9 squared is 81. So if we add these up, we get 225 is equal to c squared. And the last step of the Pythagorean theorem is to square root. So we get 15 as c. So what that actually tells you is that the straight line distance from this point to this point is exactly 15. Therefore, the rounding to the nearest tenth was not necessary.